Okay, hello everyone. I'm going to go through the Ponchon Savait's method very quickly. I've talked about this before, but I'll try to add some new or some additional information. The description is described in detail in Tribal's mass transfer operation textbook, so please refer to it, but this is just to help you in your reading. I'll describe very quickly two methods. The method of using the enthalpy diagram along with the y versus x equilibrium diagram to develop the stages directly. And the second method is to develop the nonlinear operating lines for the enriching stripping sections. And then you can use a method similar to the McCabe-Thiele stepping. So to start with, this is the enthalpy diagram versus the y versus x concentration diagrams. So this is the vapor equilibrium enthalpy, and this is against the liquid enthalpy diagram. So initially, we specify normally the reflux ratio and the distillate concentration. In terms of flow rates, normally we specify the distillate's flow rate, or alternatively we can specify the feed's flow rate. So let's assume that this is the distillate's concentration somewhere here, ZD, and the feed concentration, let's say it's somewhere here, about 0.4, and this is about 0.9 something. So we can draw a vertical line from each of these compositions, and the intersection with the vapor equilibrium enthalpy will be the enthalpy, or the position of the enthalpy of the vapor leaving stage 1, G1. So that's our starting point. To develop the staging technique, we have to specify two reference points. The difference point for the distillate, which is delta D, which falls along this vertical line here, but it's not specified initially. And we also need the delta W. Again, we have to find out the position of this. Part of the specifications is the distillate's condition. Is it going to be a vapor-liquid mixture, or is it going to be a subcooled liquid? For example, in this case, let's assume it's a subcooled liquid at a position here, D. We can determine that position based on the temperature and the enthalpy, which can be calculated from the temperature. And the feed, again, you have to specify the condition of the feed, and let's assume it's over here. So based on so it's a subcooled liquid, the feed is subcooled liquid, and based on its temperature, you can find this enthalpy. So these are your starting points, and still we don't know the position of delta D. To find delta D, we have to do a material and energy balance around the enriching section and the condenser. And you will end up with a relationship like this. The reflux ratio is equal to the difference of the enthalpies between delta D, the point delta D, and G1. So delta D will be somewhere here, which is unknown, and D1. So that difference divided by G1, the enthalpy difference between G1 and D, that ratio will be equal to your R. But we already know the position of G1 and D, so we can measure it. So we can do it graphically, actually, here. So we're going to measure it, and that's 2.5 centimeters. And let's assume a reflux ratio of 2. So that can be used to find the length of delta D, of the line delta D, G1. So it should give us a length of 5 centimeters. So we measure from G1 a distance of 5 centimeters. And that gives you your delta D. The next step to do is to find the position of delta W. Delta D, F, and delta W will fall on a straight line, so you just draw a straight line between them. The intersection here will give you your delta W. So we finished with the first step. Now, also another important point is the intersection with the liquid enthalpy line here. And that point, let's call it T. So it's a transition point. Now, the first technique is to calculate the number of stages using the enthalpy diagram directly. So what you do is you start with G1, and you want to find the corresponding L1, so the enthalpy of the liquid leaving stage 1, which is at equilibrium with G1. So you start with G1, drop a vertical line to the 45-degree line on the Y versus X diagram, and a horizontal line from 45 intersection, vertical line up to the liquid enthalpy. So that's your L1, and you can connect G1 and L1. This will be your tie line, so that's your stage 1. Now we can use L1 to find G2. So the vapor, the enthalpy of the vapor leaving stage 2. So you connect that L1 to delta D. And the intersection here will be your L2 now. Since we have G2. Since we have G2, you can find now your L2. So drop a vertical line. Make sure it's parallel to this. Drop a vertical line from G2 to the 45-degree, then horizontal to the equilibrium, then vertical again. That gives you your L2. Again, you can draw a tie line between G2 and these 2 points are at equilibrium. That will represent your stage 2. We have L2 now, we can find G3. Another connection to delta D, that's your G3. Now we can find L3, vertical line. It's not very vertical. Make sure it's parallel to this. Okay. Then I'm doing this very quickly, but you have to do it much more carefully. Vertical. So that gives you your L3. Now your G3 and L3 are at equilibrium. Now we can find your G4, now L4, okay. Okay, another vertical line, it's not very horizontal. Now, as you can see, this is L4. So G4 and L4 are at equilibrium. So this is stage 4. Now this stage is crossing the intersection, or the line joining delta D to delta W, and it's, L4 is past T. So this is actually your feed tray. From now on, we have to use delta W to find our G's. So we continue the same process, but now using the second reference point. You continue the same process. Now this is your G5. Again, vertical, and so on. Continue the same process. G5. This is your L5. So it's stage 5. Now you can get your G6 and L6. As you can see, we've gone beyond the XW. So this will be our final ideal stage. So this is your stage 6, this is your L6, stage 6. And we've gone beyond the XW, so this is your final stage. So we finished with the state, the determination of the number of stages. So this is the first method. The second method is to find the nonlinear operating lines for the enriching and the stripping sections. And then you can use that to draw the steps using just the Y versus X diagram without using the enthalpy. And you should end up with the same result as the previous method. And to do this, we do the same thing. So we start with finding again the delta D, which should be 5, and F connected with F. Find your delta W. Okay. And then you start as follows. You drop random lines from delta D. And what you do is so that's the first line. Similar thing, and then horizontal. And then what you do here is you take that the intersection on the liquid line, drop a vertical line from there, and draw the intersection here. So that's your first point, or one of the points actually, not the first point. The first point will be at X, at Z, D. And draw another line here. And then draw a vertical line from the vapor enthalpy, horizontal, and another vertical from the liquid enthalpy, and the intersection here with the horizontal line. That will be your second point on your another point on your nonlinear operating line. So again, drop any line, any random line, okay, from delta D, and take the first intersection with the vapor line, drop a vertical line to the Y versus X, to the 45 degree, then a vertical line, and you drop another vertical line from the liquid intersection and drop it. So that gives you a third point. Another point, of course, will be at a line joining delta D with delta W. So that will be the intersection. of the two operating lines. So we drop a line here, vertical, horizontal, then another vertical line. So that gives you another point. And you continue the same process until you reach the pinch point, which is on the equilibrium line. That's another point. And you can draw a line. You have to draw many lines to get it more accurate. And you continue this until this is your pinch point. And this is the intersection, right, between the two operating lines. Now, the second operating line can be drawn from delta W. You draw random lines like this, and you repeat the same process. So from the vertical lines of the vapor, horizontal, and then you get the intersection. Okay, somewhere here. The first point will be, of course, at the XW, and then you draw another random line, drop a vertical line, the 45-degree line, then a horizontal, and then another vertical line from the liquid, enthalpy, and down to here. So that gives you a second point. And you continue the process. Draw a third line. You can draw as many lines as you want, random lines, to get a more accurate curve. Okay, and you get the intersection, which will be somewhere here. Okay, so that gives you, and the intersection of the two lines will be here. Okay, and you continue by drawing more points until you reach a pinch point somewhere here. So you have now the operating line. So what you do is, once you have the two nonlinear operating lines, you can use a method similar to a Cape Thiele. So all you do is you start at XW or ZW, and you just draw your stages, horizontal, then vertical. So that's your stage one, then horizontal, vertical, stage two, horizontal, vertical, stage three, stage four. This is where you have the transition to the stripping section. That's more. Five. And stage six. So we have 6 stages, 6 ideal stages. So you can use either this technique, using first by developing a nonlinear operating line for the enriching and stripping section. So this is your feed line, feed stage. Or we can use, as we did before, the enthalpy diagram directly. Thank you very much.